So we said that this is true, that the force in the bolt, the tension of the bolt is equal to the preload plus some fraction multiplied by the applied load. We said that it's only true when the bolt is still compressing the material, right? Because this all hinged on the idea that we could treat the material as kind of acting like a spring that's helping us resist. It's working with the bolt to resist the load. That sounds weird. That's why we talked about how, a preload due to gravity on a spring, it seems like, oh, this shouldn't resist this motion, but it does because it's preloaded. In the same way, when this material remains preloaded, the spring of the material helps us resist that load, and that reduces whatever the load is on the bolt by a factor of c there. Okay, so that's only true as long as the material is compressed. When the material is no longer compressed, if the material were to gap here, if the force in the material were to go to 0, then that would no longer be true. So that's another condition that we need to check for. We need to check for making sure that the bolt's total stress doesn't exceed its proof strength, but we also need to make sure that the material doesn't gap. And that would happen if Fm goes to 0. Okay? So condition, we're talking about failure of bolts. So failure of bolts. 1 would be proof, yield exceeded. And that's when the force of the bolt, Fb, the total force in the bolt, divided by the tensile stress area of the bolt, is greater than or equal to the proof strength. I think it's called SP in the book, right? Well, the second thing we need to check for is that the joint doesn't gap. Because then FB would no longer follow this relationship anymore. It's going to start taking all of the applied load. All right? When does the joint gap? It gaps if the force in the material, the compressive force, it's initially compressive, it's negative due to the preload of the bolt. It gets more and more positive, closer and closer to positive, as you add PM, which is 1 minus C times whatever that F is. Okay? Because we're pulling on it. We're reducing the compression it has. When it goes to 0, the joint begins to gap. So that happens if Fi is equal to PM, which is F times Km over Kb, well, 1 minus C. Let's use 1 minus C here. Because then this would go to 0, right, if those two things are equal. So at what force does that happen? That happens at a force F is equal to whatever the preload is over 1 minus C. So you need to make sure that your preload is high enough so that when you get a high applied force F, that Fi over 1 minus C, when this happens, your joint will start to gap. So we need to make sure that the total applied load, we need to make sure that actually another way to look at it is that the preload then needs to be greater than or equal to 1 minus C times whatever your force is. That's another way to look at it. So let's talk about safety factors. All right. What is the safety factor against yield? Well, there's two ways to look at it. One way to look at it would be that we want the force divided by AT to be greater than or equal to SP over some safety factor. We'll call this N, well, let's see, what does it call it in the book? It calls this NP. Okay? So what is our safety factor then? Our safety factor in that case, NP, is going to be equal to SP times AT, tensile stress area, by the way, over FB, which is C times F. Oh, no, plus Fi. So over C, that joint stiffness coefficient, times F, the applied load, plus the preload in the bolt. That's what our safety factor against proof load being exceeded is. Another way of looking at it, though, and there's a different way of defining the safety factor. Instead of defining the safety factor this way, we can apply a load factor. We're saying that, let's show what it looks like, okay? It says that the total force in the bolt, let's look at what the force in the bolt is made up of. Force in the bolt is made up of the preload plus C times some applied load, right? C times F. That divided by AT has to be greater than or equal to SP. But instead of applying, one way of looking at it, this one here, is that we've applied the factor on this whole force in the bolt and said how many times can we increase that total force in the bolt such that the proof strength is exceeded. Another way of doing this, though, is instead, we know what the preload is. We don't need to put any factor on top of that. Let's just put our factor on, let's make this plus sign smaller. Let's just put our factor on N right here, NL we'll call it, the load factor. We're only going to put it as a factor on the applied load is really what we're doing. C times NLF. How much can we increase the applied load such that our stress gets greater than our proof stress? And in that case, when we solve this through, we need to solve for F here. Then we get NL is equal to SPAT. SP times AT. We're going to have to subtract FI. And then we're going to divide that by C and NL, or C and F divided by CF. Okay. So those are two ways. So if I ask for load factor, we're talking about this. This is the load factor against yield, or the proof strength being exceeded. And this is just the regular old safety factor on yield. Safety factor for joint gap is, let's see, well, let's say that we would increase that force by a certain amount, right? How much can we increase the force? And, well, what is it called? Factor against joint separation is N0. How much can we multiply F by such that that will equal Fi over 1 minus C? Well, then fine. It's as simple as, and that means that N0, our safety factor against joint separation, is just Fi, the preload, divided by the force times 1 minus C. All right, so that is our safety factor against joint separation. And of course, we can also define a safety factor against on fatigue, and it goes through the development of that in the book. It's really the same concept. If you just think about fatigue with the Goodman diagram, and you think about, okay, what is my maximum force in the bolt? How high does this get up to? How low does it get down to? Those are my minimum and maximum forces. I can figure out my minimum and maximum stresses from that. And you can kind of go through the math and figure out what, all the same sorts of things, safety factor on fatigue. So I'm not going to go through and derive it separately because it's really no different than just applying the concepts of fatigue to this situation. You know what the forces on the bolt are now.